Yes, I'm here, ready to talk.
Thank you, Ed. Go ahead.
Let me share screen. Well, good morning, everyone in China. I want to thank you for a very well-organized and very interesting meeting. Over the years, people in the cold fusion field have been trying to discover a material that would allow people to investigate the effect reliably and with ease. And the so-called lab rat that Mike Millage identified. I think I have been able to make such a material. And I have been using that material now to study the effect of temperature on the heat production from LENR. The results of this work are totally consistent with the model that I have been advocating now for the last couple of years. And we'll talk about that model a little bit. The material that I'm been using and the material that is makes the LENR effect very successfully is very simple to make. It's made by just simply cold pressing palladium powder in a steel die under high pressure so that it creates a disc. In my case, the disc is about 1 centimeter in diameter and about 2 millimeters thick. I drill a hole and a platinum wire is put through to make electrical contact to study this in an electrolytic cell. I've studied this material both in the electrolytic cell and in gas loading. Now, the material is made, as I say, by cold pressing, and then it's heated to 900 to 1,000 degrees for several hours to solidify it. I mean, before that, it's easily broken. After that heating at a high temperature, the material is very reactive to deuterium, and it loads quite well, by the way. But it does not make any excess energy when the sample is heated to higher temperatures. That requires the material to be oxidized. And that can be done a number of different ways. The method I use is by heating it in air above 400 degrees for several hours and then cooling slowly in air. The conditions, the variables, I'm sure can be combined in such a way as to produce a sweet spot. However, I don't have the facilities to identify that effectively, but the parameter space is sufficiently broad that it's fairly easy to make a sample that will produce the excess energy when heated. This is a typical solid piece of palladium that I also have studied in the same way. The solid palladium comes to me being active largely by accident. There's nothing I can do to make it active. It just simply shows up that way, and I have been lucky enough to have to acquire a number of pieces that were active. The pressed material you can see is really quite porous. I achieve about a 50% density compared to solid palladium. The excess energy is measured in a calorimeter, a Seebeck type calorimeter. You can see it in the open condition containing the electrolytic cell. The calorimeter consists of a aluminum box that is cooled by flowing water to 10 degrees centigrade. The inside surface is covered with 54 thermoelectric converters. As a result, any energy that's made inside the box has to pass through these converters to leave, and in so doing, it creates a voltage, a Seebeck voltage, which is measured. the cells are sealed and they communicate with us through a small tube to this apparatus on the right. This is a reservoir containing oil that is displaced by the oxygen that is generated when the deuterium reacts with the sample. And that displacement allows me to measure the volume of the oxygen that can be then converted into the D to PD ratio of the sample. The picture on the left shows the calorimeter containing the gas loading cell. It's possible to change from electrolytic approach to gas loading without making any change mechanically or electrically. So it's a very simple matter to go from one to the other. Each cell is calibrated separately. This is a picture of the open electrolytic cell. It's a Pyrex, made of Pyrex. It's surrounded by a resistance wire that is used to heat the electrolyte to the temperature up to 90 degrees. The cell contains about 35 milliliters of D2O, to which lithium has been added to make an electrolyte. The anode is platinum. There is an RTD device in a sealed tube that's used to measure the temperature of the electrolyte. This is sealed with a Teflon top. The cell contains a recombiner catalyst that converts any extra deuterium and oxygen back to D2O. That assembly is shown here, extracted from the cell. This is the recombiner you see. Inside, there's a tube containing an RTD that allows the temperature of the recombiner to be measured. Any gas leaving the cell has to pass, allowing any extra oxygen and deuterium to react, thereby heating the recombiner, and then any extra oxygen passes between the two tubes and leaves and goes over to the apparatus that I showed previously. This is the gas loading cell. This cell is also made of Pyrex. There's a resistance wire wrapped around it that allows it to be heated up to 300 degrees. The sample sits on a pedestal. There's an RTD in the pedestal that allows the temperature of the sample to be measured. This is sealed, evacuated, and then backfilled with deuterium. Because this only contains 17 milliliters, and the pressure is that I backfill to is 1 atmosphere, the maximum D to PD ratio that can be achieved under these conditions is 0.01. In other words, the material never leaves the alpha phase. Here's examples of some of the data that's taken when these measurements are made. This is an example of a typical calibration. This is a plot of the applied power. It's applied to the resistance wire as a DC current. And this is the resulting Seebeck voltage. These points are taken going up in temperature and then coming back down. 90 minutes is required between each point for the Seebeck calorimeter to reach equilibrium and a constant temperature. The data is taken every minute. So the first 80 minutes, it reaches constant temperature. Then the last 10 minutes, it is at constant temperature, and those points are averaged to give these points. Because of that delay, the time between this point and this point was about 22 hours. The residual is the difference in the measured value and the calculated value based upon a least squares fit to the equation to the data. And you can see that it has a normal scatter, which is approximately 5 milliwatts over the entire power and time. This gives a good feel for the amount of random scatter in the data. When a sample is measured in the electrolytic cell, a tenth of an amp is applied to it. That results in a negative excess energy because energy is being used to decompose the water, and only a small fraction of that is returned to the calorimeter when the deuterium reacts with the palladium. So it starts with a negative value, and as more and more deuterium is added, this value approaches zero when the deuterium has fully loaded the palladium. The temperature of the recombiner allows the rate of reaction to be measured. This is the fraction reacted. At the beginning, every single deuteron that is presented to the surface by the current is absorbed. And that continues for a short time, and then the deuterons start to be rejected. And they continue to more and more rejected until finally, when the sample is fully reacted, every single one is rejected, and there is no subsequent reaction thereafter. During that time, I can measure the D to PD ratio two different ways. One using the orphan oxygen, which is shown in red, and the other by using the recombiner temperature. These two very frequently show identical result. And when they do, that gives confidence that the ratio is being correctly measured. When the sample, the powdered sample, after it has been oxidized, is exposed to deuterium gas, and this is exposed in a large enough cell so that there's a significant amount of deuterium available, the delta T, that is the difference in temperature between the inside and the outside, rises rapidly as energy is being generated as the deuterium reacts with the oxide. And that reaction continues and drops off as more and more of the oxide is reacted until the deuterium starts to react just with the sample, the palladium itself, and the composition continues to rise. Because the cell that I'm going to be using to show you shortly contains only 17 milliliters, the composition never goes above a value approximately here. So we're always down in this region here. Somehow or another, oh, there, I see what's wrong. Okay, well, let's look at the data. Here is a plot of the log excess power measured using the calorimeter against 1/T. This is the temperature measured in the cell. And I call your attention to the blue points labeled B. This was a sample of the pressed powder that had been oxidized, and then it was reacted in the electrolytic cell at 1/10 of an amp until it was fully loaded. And this was the amount of power that was measured. Then it was heated using the resistance wire wrapped around the outside. And it was heated going up and then coming back down and returning to the original temperature. And you can see that there's a linear relationship here. All the points are very consistent, and this one is off the line. This initial measurement was made with current being applied, and that current caused the composition to be, the D to P ratio to be 0.85. But when the current was turned off, as it was heated, it deloaded. But again, the current was turned off and it was heated up and then back down. This was done 3 times. Each time more was lost until at the final occasion for heating, the composition had dropped to 0.46. But you see all of the data, regardless of its composition, regardless of the fact that no current was being applied, all of this data falls on the same line. And there's a break-in slope to a different slope where the temperature has a different effect. The point shown in A was another sample made the same way, but as chance would have it, it produced less excess power. But nevertheless, it was studied the same way. Again, it was loaded in the electrolytic cell. This time it was loaded to 0.81, and it was heated and then cooled. You can see that the data agree very nicely with this because this line here and this line here are exactly parallel. Years ago, I had a sample, a solid sample, that had, quite by accident, was found to be nuclear active. And at that time, I was able to heat it. And you can see when it was heated and then cooled, it produced these points. I was not studying it with care as I presently do because I didn't see the importance of this. But you can see the data, even some years ago, is parallel with this that was taken recently. This line and this line are parallel. In 1994, I had another sample that made quite a bit more excess energy. I studied the effect of temperature, but over a very narrow range, which by chance happened to fall in the transition zone between these two effects. The least squares line, therefore, is partway between the fit of the two behaviors on either side of that. Now let's look at the power produced by a pressed palladium and compare the electrolytic cell with the gas loading cell. This particular piece of press was loaded in the electrolytic cell and then heated. And when current was applied during that heating, these points resulted. The electrolytic current was turned off and it was heated again. And I got these. So the sample was improving to some degree. After this study, the sample was removed from the electrolytic cell, placed in the gas loading cell. The gas loading cell was evacuated down to 5 × 10⁻⁶ torr. It was backfilled with deuterium to about 1 atmosphere. And then that cell was heated in the calorimeter. It produced these points going up and back down. So you can see that gas loading and electrolytic loading show essentially the same behavior. Even though the composition during the gas loading was 0.01 and the composition during the electrolytic study was much higher. This data shows the same interesting behavior we saw previously if it is replotted. The data on the left side is exactly the same as the data on the right. Here we have the log of excess power against 1/T. And you can see now very clearly there's a region at low temperature where all the values show a similar slope, and then a transition to values that have a different slope, but again, very consistent with each other. Here's a sample of solid palladium that I had once again studied years ago, 2018, in the electrolytic cell. When I heated it, these were the values that I measured. I took it out of storage just recently, put it into the gas loading cell, again, evacuated it with doing nothing else except evacuating it, backfilling it with deuterium, and then proceeding to heat the electrolytic cell. The value was somewhat scattered. It went up along this line, and then once the temperature got to 200 degrees, suddenly the power went up, and it then came down on a new line. So clearly, the conditions in the solid palladium are not as stable as the conditions in the pressed material. Here's an example of nickel, which was particularly active, and you can see it made power up to 0.6 watts with 1 gram of nickel. Again, this is nickel that has been pressed and then activated. The activation process for nickel is a little more complicated than for palladium, so I won't go into that. But I want to show you because of the behavior, because this is really interesting. Again, these points were taken going up and then going back down. You can see there's very good internal consistency. But the shape of this doesn't reveal anything in particular. It's important to know that, too, that at low temperatures, essentially no excess energy was detected. It had to be heated in order to see this. And I suspect that a lot of the failed experiments that people have reported when they ran at modest temperatures would have been successful had they simply heated their samples. But if we take this
5 minutes, Ed.
If we take this and replot it, you can see that, again, we have 2 different behaviors with different slopes. Okay, so how would we explain this? Well, let's make a simple assumption. Let's assume that the LENR power is limited by the rate at which the nuclear active environment can be refueled by deuterium. This is based upon pure logic. The deuterium is being used up by the fusion process. Somehow or another, it has to be replaced. The source is in the surrounding lattice. In order to get from the surrounding lattice to the site where it's fusing, it has to diffuse. So therefore, the activation energy that we calculate based upon the heat behavior should match the activation energy for diffusion. The activation energy for the LENR effect is 29. We can calculate the activation energy for deuterium and palladium is 23. And in lower concentrations of deuterium is 25. So you can see they're close. They're not identical, but it gives a certain amount of confidence that this may be, in fact, the mechanism that is causing the higher temperature effect. The pressed powder and the gas, however, has a much lower value, with both palladium and nickel having exactly the same value. This would suggest that they're getting their deuterium not from the surrounding lattice, but from the gas directly. Well, there's several conclusions. Palladium can be caused to produce LENR equally well using electrolysis or gas loading. Therefore, the conditions uniquely created by the electrolytic action are not required. The temperature has 2 different effects with an obvious transition between the regions. The LENR process is sensitive to the D to P ratio only in the low temperature region. This is contrary to what Mike McCubry and other people have determined, and I can explain what might appear to be a conflict. In the high temperature region, the LENR process will function at ratios as low as 0.01. The LENR effect is easy to produce using pressed powders or palladium or nickel. Other studies have been done, and they have come to the similar conclusion that the diffusion is, in fact, the limiting phenomena in the high temperature region. And if I have a few minutes left, I would like to summarize my gap model, which helps explain what I've seen. Sites must form in which clusters of deuterium or hydrogen can accumulate. These sites are called the nuclear active environment. These sites are physical gaps having a critical dimension. They are created in solid palladium by stress release when it reacts with deuterium. This process is sensitive to the D to P ratio. That's what Mike McCubry and other people have seen. Also, they are created by the pressed powder in contacts between the particles. This process is not sensitive to the D to P ratio. anyway, the sites fill using Gibbs energy. In other words, the filling process is a total chemical process. There is nothing novel or unusual about it. However, once these sites become filled, for reasons that we don't understand, they can experience fusion. And the power is produced by the sum of the energy produced by each site. Okay, I'm sure you have many questions. I have to apologize because my hearing is not very good. And so I have a hard time understanding some people. But my wife, who's sitting here, her hearing is very good. And so I might perhaps have to ask her to tell me what some of you have said so I can provide an answer. But thank you for listening.
Thank you, Ed. Eugenie, did you have a question or did you change your mind?
Thank you very much. Are you listening to me? Are you listening to me?
Yes.
Yes, we can hear you.
Okay.
Yes, you're listening.
Thank you for a very interesting report. Mr. Storm, you reactor allow to do a pressure higher or larger. Are you trying to do this?
Have you tried to do higher pressure?
No, I have not tried higher pressure. My cell is made of Pyrex. It won't take very much additional pressure. I have put in a couple of atmospheres, and I've also put in much less than 1 atmosphere. The applied pressure seems to have no effect whatsoever on the behavior.
Thank you very much.
Okay, Jacques. You should be able to unmute. Oh,
Yes,
you were unmuted for a second. There you are.
okay. So thank you, Ed, for this presentation. You know, this is very impressive. I would like to know 2 things. Did you try also nickel with hydrogen, regular hydrogen, instead of deuterium? First, and second questions, you know, you say that it's more difficult to activate nickel. When do you think you will be in a position to explain to us how you can activate nickel, please?
Okay, there are 2 questions. The second one was, when do you think you'll be in a position to explain how to activate nickel?
Well, I'm working with a number of laboratories presently in order to explore this discovery and this material. Once the necessary arrangements, both legal and otherwise, are made, I will share what I know and hopefully work with them to make the process even more reliable. But so I don't know precisely when I could make more information public. That will depend on the interests of the collaborators.
The other question he had is, did you try running it with hydrogen instead of deuterium?
Yes, I have the nickel sample. I applied hydrogen at one point. After it had run with deuterium, I pumped out the deuterium to a good vacuum, put hydrogen back in, and then ran it up through the same temperature. The light hydrogen initially started to produce less energy. It gradually increased in the amount of energy, and then it came down on another line somewhat higher than it started, but below that for deuterium. Then I pumped that out and put deuterium back in to see whether or not there was a permanent change. The deuterium results came back very similar to what they were before, but slightly displaced. So the light hydrogen does in fact produce excess energy, but less than that produced by deuterium.
Thank you.
Thank you very much.
Okay, I'm looking, people are keep changing their mind about raising their hand. Lynn Bowen, can you do a quick question?
Yes, Dr. Storms, I was wondering about the nuclear active environment, and in particular, do you have a rough estimate of what that critical dimension is? You mentioned that there was a gap of a critical dimension. Do you have any idea, a rough estimate, what that might be?
Yes, I estimate it to be about 1 nanometer, plus or minus, maybe 1 nanometer to 2 or 3 nanometers, somewhere in that vicinity. If it's too small, it acts like the dimension of the crystal itself, which is 1/10 of a nanometer. If it's too big, the molecule, D2 molecule, can form in preference to this particular rather strange chemical compound that is capable of fusing. So somewhere in that neighborhood, maybe 1 to 2 to 3 nanometers. It's on a very small scale. That's why it's so difficult to find.
Okay, and what would you say in your pressed samples? Would you say that the material is 50% gap and 50% palladium? Or would you say it's 1090? Or how would you estimate how much of it is a gap and how much of it is crystal?
I can measure the density by measuring the physical dimensions and then weighing it. And I can compare that density to solid palladium. So the gaps are about 50%.
About 50%, okay.
So,
And sorry, Ed, we're gonna have to move on.
and it's the pressure.
He said he said he has to move on.
Okay.
All
Yeah.
right,
Thank you.
Send me an email. I'd be happy to answer any questions by email.
Okay,